This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 47, a roundtable discussion about what is exciting in the solver for Ansys 2019 R3, mechanical and mechanical APDL, and a look at news and events in the Ansys world. Hi there, my name's Eric Miller. I'm one of the owners here at PADT, and welcome to our podcast. Greetings from Phoenix, Arizona. It's a lazy Sunday morning, and I'm up in my son's old room. He's off to college, so it's the quietest room in the house. I've spoken from here before. I just sometimes wonder how embarrassed he would be to know that his old, at least in his eyes, his old father is using his former desk to record a podcast. I don't know what he feels about that, but he's gone. It's not his choice anymore. It is August 22nd, so not long before we take that downhill slide to the end of the year. Halloween, followed by Thanksgiving, and then the holiday break leading up to the New Year's Day celebrations in the start of 2020. And a lot has happened in the past 9 months. It's been PADT's 25th anniversary, and many things have occurred in the world of politics and economics and technology and science. In the Ansys world, I think that this year we'll look back on and see the biggest thing that happened in the Ansys world is the purchase of LSTC by Ansys Inc. And we're going to talk a lot about that in the second half during the news portion of this podcast. And we talk a little bit about it in our interview because I couldn't resist discussing it with our tech support staff. And speaking of that, let's go ahead and get started on that. We have these incredible FEA solver that is inside the Ansys Mechanical APDL. That's the solver that Ansys Mechanical uses. And lots of new things have been exposed in Contact and speeding up the solvers themselves and new elements, new capabilities. So we're going to really focus on that during this discussion. It's because mainly we decided to catch up because in a lot of new cool stuff at Ansys 2019 R3. It's faster and there's just more stuff in there. So let's take a listen and hear what Ted, Joe, and Doug have to add to what's coming in, or what is here now in R3 of 2019, Ansys Mechanical. Welcome, everybody, today to our discussion on what's new with Ansys Mechanical Solver, Elements, and Contact Elements. And we're going to be talking about what just came out in R3 of 2019 with the new naming scheme. It's properly, I guess, Ansys 2019 R3 rather than Yoda speak. And today I have with me Ted, Joe, and Doug. And so we'll go in that order. Why don't you introduce yourselves and let us know what you do here at PADT.
This is Ted Harris. I manage our simulation support group here at PADT.
This is Joe Woodward. I'm the lead trainer here at PADT.
This is Doug Oatis, and I'm the lead mechanical engineer at PADT.
And you are calling from Colorado, correct, Doug?
Last time I checked.
That's when you checked.
Yes. Be here all night.
That's right. Yeah, don't forget to tip your waitress. And then Joe and Ted and I are all in the same building, but we're all calling from our desks to get a little bit better sound quality than sitting around on microphone. So hopefully that'll make it a little bit easier for everybody to hear. So I'm excited. This is kind of the core, the foundation. It's what Ansys is all about is the, what you can do with the solver and what you can do with contacts and, of course, the element technology within. Newer users may not be aware of kind of how the code works. So maybe a little bit of background is that, when you're in there creating meshes and telling in mechanical, telling the model what you want it to be done, under the hood, what it's doing is assigning element types to it. So you'll hear us call out numbers or names of elements. Those are the equations that is a discretized behavior of the element that we're going to go ahead and be solving. And of course, we take all those elements, assemble them into a matrix, invert the matrix, solve the unknowns, and come up with answers. And Contact, everybody should be familiar with, but just in case, Contact is an element family that says, I can have two other groups of elements that I sit on top of, and they can be open or they can be closed. They can be touching or not touching. And how I transfer loads, both perpendicular and parallel to that contact surface, are dependent upon the force that is between those two, and all sorts of fancy stuff. That if you do any kind of assembly modeling, you should get a geared head around contacts. We won't do that here today. So let's get started with kind of my typical question when we talk about what's new. We'll start with Doug. We'll go in reverse order. Doug, what's your favorite new feature that came out in R3?
Oh man, well I just installed it, so I'm a little I'm a little behind the curve. But yes. Just one of my features in that one of the element types that has been kind of introduced or at least rolled out more broadly is the like the reinforcing elements. And so if you've ever done a reinforcing simulation, you're trying to essentially simulate some embedded object, whether it's a plate, sheet, rebar, anything like that. And, back in olden times, in order to simulate that, you pretty much went blind just splitting your geometry so that you could essentially expose these fake surfaces that you could, pave certain features with. And on the structural side, we've had the ability to essentially reinforce elements without having to go blind and cut up your geometry like that. And it's also available on the thermal side now. And so rather than you having to, split up your geometry into, specific ground planes or to expose, copper versus insulated materials, it's essentially like a ghost skin that kind of overlays the existing element that solves for temperature and allows you to essentially add kind of these additional degrees of freedoms that get mapped into the element. So just, anytime you don't have to go blind to do a simulation, I'm usually a fan of.
It's letting us, when you look at some of these more complicated, I use the term composite, but there's structures that have other structures inside them.
When you have like a high aspect ratio of detail versus global model, that's,
So it can be a nightmare. So rebar would be a great example of that. What's another usage of those elements?
So like I said, printed circuit boards, you don't necessarily have to split up everything on a layer by layer basis. Obviously, the more closely the discretization gets to the actual, the better. But if the nice thing about thermal response in a PCB is you usually don't need that high level of detail of where exactly a trace ends and where the insulation begins. And I mean on the structural side of things, like you said, rebar, any type of reinforced concrete where you have those mesh that are laid. Obviously, I don't do a lot of making reinforced concrete because I'm not using the right words. But so those kinds of things where you basically have something embedded in something else.
Apologies to civil engineers out there. But I mean, this has always been the kind of the bugaboo with modeling those complicated printed circuit boards is you just can't get that detail in there. You don't want to get that detail in there. So this is big, and it doesn't really change the global results that much either. It's pretty accurate. Good. What about you, Joe? What's your fave?
I think mine would have to be the not really the addition of the new coupled field elements. They've been in there, but they're allowing now in Workbench to access those. So instead of doing just a single sequential thermal to structural model, you can access the coupled field models and do your thermal and structural at the same time, so that if your thermal deflections would open gaps and things like that then change your heat flow paths, that can all be done within Workbench now.
Yeah, so if people aren't familiar with that, if you've only ever used Workbench, when you want to do these multi-physics solves, you've always had to solve one physics, take the loads and apply them to the next physics, which is what we call load coupling, and then iterate till it converges. But the solver has always had the ability to solve for different degrees of freedom at the same time. So say structural and thermal at the same time. So those are now being exposed. So you don't have to write snippets, or I guess the most important thing is now we can post-process them too. So
you don't.
Right.
There was an ACT extension that kind of allowed you to do that.
Yeah.
And I think the funny thing here is, you could do that in a PDL. Mm-hmm. You could also do it in AIM.
That's right.
And mechanical was the middleman that didn't have this functionality. So it's kind of nice to have that there.
Does it create? I haven't looked at it yet. Does it create a separate tree? So, or do you just, when you add a result object, it lets you add temperature and stress?
I think you can add both temperature and stress to it. I haven't played with it yet.
Yeah, it's just more buttons.
Right.
Yeah.
Right.
Yeah, it's more options
there. It allows you to put the structural and thermal loads on it.
Nice. That solves faster. Not that these solves are that slow right now, but that's a cool thing. What degrees of freedom? It's doing thermal and stress. Does it do other ones as well?
I think right now it's just thermal and stress.
Stress, which is 90%.
Right. You can still do like electromagnetics. Your
the low frequency
thermoelectric.
Right. Yeah. Thermoelectric with command snippets.
The voltage.
So I assume right. So I assume those will be in next iteration around. They'll add those in.
What was the other one that I liked that I used to like to use? We use it for fluids migrating through cracks. It's a thermal analogy, right? So there's another degree of freedom for that in those elements.
Talking about porosity?
Porosity, yes, thank you. That's the proper term. So that'll be a nice one to add as well.
That was all part of that massive geomechanical model inclusion. Was that 19.2 or R1? It was a couple revs back, but
it was a couple revs back.
Yeah, they big one.
It was the one thing that another code that shall not be named that a lot of Scandinavians like that it would do that people can do with Ansys. So we had all these customers that owned a seed of that other code to do the porosity, and now that we have it, it's kind of nice.
More civil engineering terms that we're mangling.
Well, and using it in fluids to get in between printed circuit board chips, like in between layers on printed circuit boards. Use it for that as well. That was what our customers were screaming about, was liquid kind of weaking its way in. Ted, what's your favorite?
Okay, so the one I'm going to talk about is one that actually isn't new at this release. It was new at the last release, but it's been enhanced. And that is the ability to have the code split up contact regions to take advantage of multiple cores during the solution. So, going back many, many years, Ansys has been able to solve in parallel. Probably the modern era, if we want to call it that, maybe started in version 11 with continual improvements ever since. But one thing that hadn't been implemented was the ability to take the contact regions and have them be split up to take advantage of multiple cores. So if you had a model that had a lot of contact on it, you did not see as much of a speed up. In fact, sometimes we would end up running SMP instead of distributed because the contact was basically all being solved on a single core. So starting at R2, I believe, the code automatically starts splitting up contact to take advantage of multiple cores. And that's been enhanced in R3 in that it'll do an initial splitting, but then it'll take a look at it again and produce some sub pairs to help more evenly distribute the load among the cores being used for the solution. So that adds an additional benefit to distributed solves when you have lots of contact involved.
Mm-hmm. So big models with lots of contact where you can split it up. In fact, a lot of this stuff we'll cover in a webinar that you're doing next week. Is that correct, Ted?
Yes, next Wednesday.
Next Wednesday. Okay. So this will. There's some images that are in the PowerPoint presentation, and one of them is pretty cool. It's got a tire rolling across something, I guess a road. And it shows
so
how
you guys were talking about reinforcing elements, and
that's another
tire is another good application. If you're old enough like me to remember 7 around 2 wrapped by 1. You'll know what I'm talking about.
I remember those.
Yeah. I don't think my children even knew if they even thought about how a tire is made on their car. That's pretty funny. Okay, cool. So those are kind of different areas. I'll just kind of mention I'm a huge fan of rotor dynamics. I've always wanted Ansys to be a better rotor dynamics tool, and we keep adding some cool things into it. So at this release, the 178 element now allows nonlinear radial gap elements, and so this is a pretty sophisticated modeling that's used in rotor dynamics to get this nonlinear behavior of bearings handled properly, and it's pretty cool. So if and I always say this every time I bring rotor dynamics, but if you're using a third-party code or an academic code to do your rotor dynamics, you should, every time I add something, take a look and see whether we can do everything. This takes care of a nonlinear radial gap between cylinders while something's spinning around.
Including friction.
Including friction, yeah. So it's pretty impressive.
If people aren't aware, there's a lot of capability built into Ansys Mechanical for rotor dynamics. For example, you can generate Campbell diagrams, forward and backward traveling waves, and look for resonant points and things like that with what we call engine excitations. All that capability is there and built in.
Yes, there's still a lot of people using those older codes or academic codes or third-party codes, and definitely take a look and see what we can do there. I think that was the only thing that was added for rotor dynamics. What else in the contact realm? I'm kind of excited. I haven't, of course, had a chance to play with it, but it looks like they've done some better force convergence checking.
It's kind of an interesting little fix of applying a localized control, which may actually induce some additional iterations for a contact pair. But it's one of those, if you can clean up your answer early on, it makes convergence faster overall, or it cleans up the convergence behavior kind of long term. And so there's an additional kind of real constant that can be applied on a contact by contact basis. So you can apply a localized control because, overall convergence is measured on a global scale.
Right.
And so if you can, apply a localized check, especially where there's a lot of, small contact patch, that can help drive that convergence a little bit better.
So you realize that it's kind of oscillating at that area. You can go in and specify these local convergence checking, kind of smooth it all out, and that could be a pretty handy thing. Yeah.
I mean, plus that quasi-static switch, so that you can kind of do semi-explicit, or I forget the terminology, but basically go to an explicit time integration scheme for kind of high deformation effects.
Yeah, where it switches back and forth to be able to get past the convergence difficulties and then switch back to an implicit for the longer term.
Okay, right. Yeah, it's a lot more control that comes. It's pretty cool stuff. What else? Anybody want to talk about? Anything special?
Looks like in R3 they've added the ability to switch the shell normals without actually having to remesh. That's more of a MAPDL thing. If you're going in and checking shell normals on its own.
We were talking about that before we got on air. I think, Ted, you had some insight into that, having to do with third-party post-processors.
I can't take credit for that. That was Doug.
That was Doug. You guys all sound the
same. You just sign in checks. We all sound the same. Yeah. It's more from a composite standpoint of using third-party tools that, rather than us blaming other tools for not speaking our language, basically the element by element basis accepts different orientations. And so this might not sound really big, but when you're trying to apply pressures and making sure that the pressure is acting on the top versus the bottom of a spatially 2D object, it's pretty important. So it's rather than hunting through and finding that one element and then trying to redefine the IJK node orders to get the right hand rule pointing in the correct direction, you just apply a different coordinate system, flip it, and you're continue on your way.
Okay. That is kind of handy. Yeah. Very, very cool. Let me think if there's been quite a bit of enhancements on the solver side, speeding stuff up. And they give a lot of examples of that. Anything big in there that you guys think's worth sharing?
Well, I was going to say one thing that came out, I think, in R1. Was the stresses on demand, so that it's not really a speed up, but it reduces the result file size quite a bit, and then it just calculates the stresses when it goes to make the plot. Right. So the plots take just a little bit longer, but with Workbench, as you switch between plots, it's not recalculating that all the time. The way mechanical APDL did. Anyway, so a little bit longer up front is not too big a deal for smaller file sizes.
You get away from those ginormous. What we've been dealing with from really day one with the Ansys solver is because it's been around for so long. Is we would solve over on a remote machine, often in a different state, bring the results back, and you didn't really have a lot of horsepower to look at the answers on your desktop. So we would calculate during the solve and store for every integration point. And so if you've got a 8-noded element, every corner of that element had every stress value calculated and stored in the files. So the files got huge. Now I think we just store the strain information. I think that's right. And then calculate the stresses on the fly and other derived values on the fly. So getting away from these gigantic multi-gigabyte result files, which is kind of nice. What about, I think the biggest improvement that I saw on the solver side.
Well, I think that a lot of the solver improvements kind of go along with what they now support. Because typically what happens, like a new feature like Smart Fracture is introduced, but it only works on shared memory, and so basically figuring out ways to write these new features such that they can be spread across multiple cores. And so, that's pretty much what you should expect every rev is. Not only does it solve faster, which there's data to support that, but also that you're not limited in shared versus distributed for the newer features.
Right.
I'm looking at the improvements to the sparse direct solver, and it's still speeding up now at R3. It used to peak out at 512 cores. It's still getting a little bit faster at 1024. That's big for a structural model.
It wasn't that long ago that we were saying 6 or 8 cores is probably the sweet spot for a structural simulation, and that is no longer true. Definitely seeing scaling up into the hundreds of cores, which used to be the realm of CFD only,
right.
And that's no longer true. Still not seeing a linear speed up, but there's definitely a benefit of solving on those additional cores for a lot of large models. And when we say large models, we're talking about in the millions of degrees of freedom range typically.
All right. Well, and I've noticed if you look at that same graph, it's actually curving upward. So it's It's not just.
I've never seen that before. I wonder if that's a round.
That's a spline fit.
Yeah, that's what I'm wondering, because most of the charts are looking like that.
Some sort of a hardware thing. They usually kind of plateau. Yeah. So I think the takeaway is that they're. I think what Doug said is really important. Is what they're doing is different. The main stuff has always been parallelized. Now they're going through and adding other calculations that need to be done. So that if you've got something other than just a linear stress model with no contact or anything special in it, those scale well now. Like I'm looking at the LPT model, which I think is actually a model that we gave them many, 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 many years ago. It's speeding up. It runs on 256 cores now, and it's 7.5 times faster on 256 cores. So that's pretty significant. That's PCG.
The other thing to look at on those charts is the memory requirements at those high core counts also have gone down. And so that was kind of in order to use all these cores, you have to have a lot of additional resources to handle the inter-core communications. And so it's nice to see that, if you have those available, you don't have to throw in a daughter board on your workstation in order to actually use those for solving.
Yeah, that's really an important thing. So pretty exciting stuff on that. And so definitely users should take a look if they haven't looked at Parallel in a while and see if they can justify getting more cores or using Nimbix or Ansys Cloud to solve on. So if you're
on that topic, if customers go to the Ansys customer portal, and you have to have a login, but if you're a current Ansys customer, you can certainly establish a login. There is a hardware document that you can find that is updated quite frequently, and that is a really good source of information for typical hardware decisions that people are making for buying a new system. And it has some recommendations. There are 3 different physics listed, so mechanical, fluids, and electronics.
Cool.
So that's a good source.
That is really good to know. I definitely need to check that out if you're looking to get new hardware. Let's see if there's anything else that you guys have anything else you want to share before we wrap it up? I think we covered the big stuff.
One more that I wanted to mention, and that is a new capability to be able to calculate viscoelastic heating. So this is part of that coupled structural thermal analysis. It uses the 220X elements in Ansys, which are the latest and greatest coupled physics elements. So you now have the ability to calculate temperature change due to viscoelastic deformation. So for people that are simulating elastomers or certain biological materials, there might be some nice benefit there.
So it heats up as you deform it, and it'll actually calculate that heat generation and do a thermal analysis as part of it. Yeah,
right. It's coupled.
Coupled. Yeah. All right, that is cool. I did not see that one. That's a good one. How about you, Joe and Doug? You guys got anything that we didn't cover?
Nothing else I can think of at the moment.
I've got an obscure one, which is the piezoelectric improvements. So they basically added more elements are supported to do piezoelectric analysis. They can do damped modal analysis now, and energy calculations in a modal analysis. So if you remember your piezoelectrics, if you put a voltage on it, it creates a strain, it deforms, it expands, or contracts, depending on which way the voltage is going. And if you put physical load on it, if you squish it or if you pull on it, it generates voltage. And that includes, a certain amount of electric energy as well as elastic energy that gets calculated. So that's all actually in there now. So I think that's really beyond my understanding of the physics. But if you do use piezo, take a look at it. The temperature-dependent piezoelectric materials are there as well now, and there's a current-based formulation for harmonic and transient analysis. So modeling, again, this is another one of those things where people were often using a specialty code to model transducers or actuators that are piezoelectric, and we're getting more and more capability to do those native in Ansys. Anything else, guys? You still there?
We're trying to limit our scope here to just the topics covered in the next webinar. So I know we'll be having other podcasts. We'll be talking about other new topics.
Okay, cool.
There's a lot of new topics.
With the three or more releases a year, I think it's going to be 3. They come fast and furious, and they do get a little confused as to which release it is, but it's good stuff. If you don't see something that you want to know about, reach out to us, and we'll be talking with you guys soon about some other stuff. I think we've got some other discussions scheduled, so let us know. And before I cut off, I love springing stuff on you unprepared, but one of the things we'll be talking about on the rest of the podcast, I'll be talking about the rest of the podcast, is the LS-DYNA merger acquisition. What are your guys' thoughts on that?
Pumped.
Yeah.
There are many emails where I usually try not to pay attention to the business side of things, and that one was one where I was like, I may have started clapping like that guy on an airplane when they land clapping. So I'm excited about that one.
How about
my thought was it's about time.
Yeah, I think everybody was kind of hoping that this would happen and that somebody else wouldn't outbid Ansys, and it really is the perfect fit. Ted, what's your thought?
Well, my only thought was just kind of a little bit the other way. Not that it was bad or anything, but just that, the press release kind of made it sound like, Ansys users can now start using LS-DYNA, which is not true, because LS-DYNA has been sold through Ansys for many, many years. Mm-hmm. So it's only going to take that relationship and make it much, much stronger. So,
that's a really good point. The interface, as an example, the interface between mechanical and LS-DYNA has been there for a couple releases now, and it hasn't moved as quickly as we'd like to see it move.
And it was an ACT extension
before that, right? It was really powerful, and it still made building LS-DYNA models much easier. But this will speed it up.
For many, many years, if you're running mechanical APDL, when you bring up the launcher, one of the drop downs is Ansys LS-DYNA. So,
yeah, exactly.
It's been built in for quite a while.
Yeah, I'm very
as a partner with Ansys. So.
As a partner, yeah, very close partner, which is why I'm glad that they decided to sell to Ansys, and I think it's going to be fantastic. And what a great group of software developers as well that we're going to add to the Solver team. They do some pretty amazing things over there, and when it's all said and done, maybe the first official release where they've worked together, I'll get Jim on. So many of you who listen know Jim Peters, who's one of our lead simulation consulting people here, and he has been an LS-DYNA user for more years than I think we'd like to admit. I think he started using it at the same time I did, back when it was still an open source code at the National Labs. And he's just beside himself with joy because he does most of our consulting with LS-DYNA. To not have to deal with another organization when we need support or something is going to be fantastic. So very excited about that.
Yep, it's great.
All righty, and think of what implicit explicit is going to be like now that we can turn on hopefully the LS-DYNA solver at some point as the explicit solver. So that'll be sweet. All right, guys, we'll definitely talk about that more in the future. In fact, I need to go back and see if one of our predictions predicted the acquisition. I think at one point one of us said we were going to acquire LS-DYNA. So I'll have to look back at our predictions and see if that was said or not. And if not, I'll edit it in so we sound smart. But everybody wanted to know what would the big acquisition be? And everybody said, well, I hope it's LS-DYNA, but no, they probably won't sell. It's a family-owned business, but I'm so happy to see it happen. All right, we'll talk to you guys soon. You guys can get back to work. And those that want to learn more and see some visuals about what we talked about, please do sign up for the webinar, which is going to be the Wednesday, the 25th.
Yes.
I made the mistake of putting up my 2020 calendar, so I got to make sure I look at the right one. Yes, the 25th. And definitely send your questions and comments to us, and we'll talk to you guys soon. Thanks. So we often get focused on the pre and post processing in simulation because that's where we as users spend most of our time. But we do need to remember that we are pre and post processing to send simulation to the solver, and post processing what the solver produces. If we don't keep up with what is going on in the solver world, we don't stay up to date with what we can do with these amazing tools, what we can use them for, and how we can use them more efficiently or more accurately. So it's always good to look back and see what's new and different. And as always, I always recommend you read the release notes when you have time. We also have a webinar on Wednesday, September 25th. That's in 3 days at 11 o'clock Phoenix, California time. And as always, if you don't have time to listen to it live, you can ask questions, which is an advantage of live. But if you don't have time to listen live, then you can always listen to the recording. As with all of our webinars, you can go to www.brighttalk.com and search for PADT or even Ansys and find most of our stuff, old and new, including this one where you can register. And that's how you get on the list to be able to listen to it both live and recorded. Or if you don't want to go to the Bright Talk website, you can get there by going to our events page on padtinc.com and seeing that. So let's take a little bit of a break for a commercial. Enough blah, blah, blah about simulation and Ansys. Let's change the subject and talk about PADT's additive manufacturing services. You have a lot of choices of where to go to get your 3D printing done. But there is no other additive manufacturing service provider like PADT. That's because we have experience, we understand engineering, and we have know-how in the additive manufacturing space. Since we purchased our first stereolithography machine in 1994, PADT has been dedicated to partnering with our customers to make the parts they need. With our team of experts, you are not just uploading a file that we toss into a build, then sand it, and maybe throw it into a box and ship it to you. We take the time to understand what you need and what your parts are for. And then we match the right process and material to those needs. And since each additive manufacturing technology has its own strengths and weaknesses, we have 5 different technologies in-house: stereolithography, selective laser sintering, fused deposition modeling, multi-material and multicolor polyjet printing, metal laser powder bed fusion, metal sintering, and on-demand manufacturing with Carbon's digital light synthesis process. We have 3 or more different machines for each polymer process and run multiple materials on every single one, including our 2 metal machines. Because you listen to this podcast, you know that PADT's engineers are true experts in a wide breadth of simulation approaches. The same is true for our 3D printing services. Just as we are able to apply every physics to simulate what our customers need, we can apply every major additive technology in the same way and the same level of expertise, knowing the tools and understanding how our customers use what we produce. So next time you need some parts 3D printed of any kind, please come to the experts at PADT. We don't just know simulation inside and out. We are just as good at additive manufacturing. Visit www.padtinc.com. Email us at info@padtinc.com, or as always, give us a call at 480-813-4884. We'd love to help you with your 3D printing needs. All right, welcome back. Now, I don't think that the fact that Ansys hit an all-time high, its stock hit an all-time high this past week, has anything to do with the LS Dyna acquisition. I don't think that Wall Street's intelligent enough to understand the importance of that acquisition. Maybe I'm wrong, but it does show a lot of interest in the stock. So $220.82 per share. It hit on Thursday. It's dropped down a little bit to $216.57 on Friday. The market's closed, of course, for the weekend. So definitely a good run. One of the things I did notice when looking to see how much the LSTC acquisition may have been received out there is that many of the non-technical articles written about the acquisition refer to LSTC as an auto tech company. Because, as we'll talk about in a second, a lot of what people use LS Dyna for is to do crash simulation. So they see this as yet another play by Ansys, and I think rightfully so, to get into and penetrate deeper into the automotive market, something that we've been growing and growing and growing with autonomous vehicles and with fluid flow and structural, and now the electrification of all these vehicles with our EMAG products. So this is just another tool in the suite that the automotive companies will be using from Ansys. I think you also, just before the announcement of the LSTC acquisition, they announced a partnership with Autodesk. Autodesk has a visualization tool, a kind of a rendering tool for simulating driving around in vehicles. They use it a lot with autonomous vehicle training. Well, our Optis tool is now officially a partnership with Autodesk to use their visualization tool with the Ansys simulation tool, Optis, to simulate driving around and what things look like with various kinds of sensors. So more and more in the automotive space. But back to the stock. On September 20th, that's when the market closed. That was Friday. Ansys year to date, since January 1, is up 57.35%. And the S&P 500, which is the benchmark I like to use, is up only 22 only. It's pretty good, 22.23%. I usually don't look at other stocks because there really isn't another publicly traded simulation-only company out there. But let's look at who everybody else compares Ansys to. Autodesk is up 25.8%, so it's in line with what the S&P 500 has done. Dassault Systems, again, which is another large PLM tool, but they also sell the most competitive products to the Ansys suite. They're up 35.75%, so not nearly as good as Ansys. PTC is actually down year to date, 13%. So not even keeping up with the S&P 500 as they pivot towards Internet of Things and other areas. And then Siemens, which really is not even a PLM company, right? They make everything, from large steam engines to home automation systems, but they're up 2.6%. So for the year, so again, well below the market. Another tool that I was hoping to look at is MathWorks, because they're a large mathematical kind of simulation company, but they're privately held, as was LSTC until they were just acquired. But I did notice one thing when I was looking at MathWorks that I didn't realize is that Ansys has passed MathWorks in revenue. So MathWorks is a little over $1 billion a year, and Ansys, of course, is north of 1.2 billion. So that's interesting to see. That we used to think of MathWorks as quite a bit larger. We have to change our paradigm as Ansys continues to grow and adds these tools. So let's talk officially, although I've been weaving it into everything in this podcast, about the LSTC purchase. So some background. LSTC stands for Livermore Software Technology Corporation. It's based in Livermore, California. And they primarily sell and support and use the tool called LS-DYNA. And LS-DYNA focuses on and is the market leader in the space for highly nonlinear transient dynamic FEA. So anything where metal especially is being heavily deformed, it can be lots of different materials. They model earth, they model concrete, they model all sorts of things. So when your material is heavily deformed and over a short duration, so it's transient as well, pretty quick, we use LS-DYNA to solve those things. And as Ted pointed out, we've been using LS-DYNA for a very long time. Ansys has been a reseller of LS-DYNA. PADT has been a reseller of LS-DYNA through Ansys since we started. So, it's over 20 years now, and you've always been able to get your Ansys model into LS-DYNA. What we've seen more recently, I can't remember when it actually came out, but it's been over 5 years, is that Ansys Mechanical can write the file directly. We can set up our model in Ansys Mechanical now and save it as LS-DYNA. We expect all of that to improve. Some background there. LSTC was formed in 1988. When the tool went from government code to commercial. The government version, which was called Dyna 3D, was started in 1976 at Lawrence Livermore National Labs by John O. Halquist. And just like Ansys, it was started for a nuclear program, a project to model something new and different in the nuclear world that got abandoned. But it was technically very difficult, so they needed new tools, and that new tool became Dyna 3D. They needed a 3D transient simulation tool, and that's where Dr. John Halquist started writing the code. And like I said, he left in 88 to form LSTC, and over the years, it went from being used to kind of do that kind of metal deformation in the weapons world to metal forming, bird strike, airbag inflation. And I think what it's best known for is car crashes. Most of the major automotive manufacturers manufacturers outside of maybe France use LS-DYNA to model their car crashes. And it's one of the reasons why cars are so safe now. Why we have these crunch zones and all these much safer vehicles is because of the use of LS-DYNA rather than running things into walls and iterating. They could iterate very quickly in a virtual world, modeling the entire vehicle and the wall it hits or another vehicle. So very cool tool. We really enjoy using it. I first used it, I think, in 1987. I used Dyna 3D. I got the tape from some guy named Halquist that somebody actually had to send it in the mail, the request. And I got a tape back in the mail from Lawrence Livermore to run this code. And I loaded it on the backs and did Bird Strike with it back then. Soon thereafter, LS-DYNA came out and we started using LS-DYNA for Bird Strike. And it's just been a fantastic tool. Why we love it is because of the generalized contact that it has, as well as the large deformation, how it handles it so well. As a teaser, what does LS-DYNA do? We're gonna try and let me back up a little bit. When the acquisition goes through and the integration begins, as usual, Ansys will probably operate them somewhat separately for a while, and then over time integrate various portions until it's part of the development team. That can take a long time. But when everything's kind of official and we know what the path forward is, we'll try and get some folks from Ansys on to talk about where we're going with it and what's there, and talk in more depth about LS-DYNA as a tool. But if you're not familiar with it, besides doing this large deformation structural stuff, it has several fluid solvers. So we can do FSI. It does acoustics, craft propagation. It has I shouldn't say full, but it's got multi-physics coupling. So it supports many physics, including thermal, radiation transport, and some EMAGs along with the fluids. So you can do these kind of transient FSI and other multi-physics applications. It also supports some different methods besides the standard one. It does smooth particle hydrodynamics, SPH. It does DEM, discrete element modeling, which is what we use for particles. And it does element-free Galerkin, which is kind of a meshless simulation that's becoming more and more popular over time for certain kinds of problems. So these are new capabilities that we've always had through Ansys LS-DYNA, which is really just LS-DYNA sold by Ansys. Now it's going to be more tightly integrated, we hope, in the future. And we will share with you as we learn and can share what that integration is going to look like. We're very excited about it. I can't say more about it or you guys are going to unsubscribe. So we're giddy. You heard Doug's response that he was like that idiot that claps when the airplane lands. He's so happy about it. Doug's not that kind of person to get excited about that sort of thing. It's pretty cool. It's a big deal. And if you're in the structural world, you know that. If you're not, this is why we keep talking about it. And we will continue to talk about it. But let's move on to PADT news. What's the biggest news at PADT? We're really excited about the LSTC purchase. We're working towards finishing up Q3 and charging into Q4. Really nothing big to report on the PADT news side. The only other news in the Ansys world is the partnership with Autodesk on integrating our simulation tools for autonomous driving, visualization, and that is a big deal. It would have been something we would have talked about a lot more, but this is bigger. Let's see. Ansys blog. I picked 3 articles. The 3 I picked this podcast are pretty good. I'm actually really excited about all 3 of them because they look at different aspects of the Ansys world, and some are deal with things that I've been kind of wanting to see better simulation of over time, or personally I just like. The first one is the one that I personally just like. Ever since I was a little kid, I wanted a flying car. The older I get, and the more I sit in traffic, the more I want a flying car. And so there's a really good article called Self-Flying Planes Are Here. Autonomous Aircraft Are the Future. Of course, Ansys plays a big role in the design of the sensors, the control software, and simulating that autonomous system. It talks about how people do that and how they're using simulation to drive and make this idea of a self-flying plane a reality. But more importantly, I hope it will lead to flying cars. So that's my desire, why I like that article so much. Another one, since we started PADT, we've been running into people trying to do what we call lab on a chip, where you take a little bit of blood or a little bit of other liquid, and on an actual small device, you run a bunch of tests on it. And the reason why that hasn't really taken off over the years as much as everybody had hoped is that making the little chip that holds and moves the fluids around, it's called a fluidic chip, fluidic device, is really microfluidic, I should say. The proper term is microfluidic at that scale. It's really hard to do. Surface finish drives everything. Well, this company has developed a methodology to mass produce almost the same speed as injection molding using some very sophisticated manufacturing methods. And they derived those methods to make these microfluidic chips using Ansys tools, the electromagnetic tools, because their process uses magnetic fields as well as fluid flow, as you would imagine. So it's a really good article. It's called New Microfluidic Chip Fabrication Techniques Simplifies Mass Production and Improves Reliability. So do check that out if you're at all involved in microfluidics, or even if you're just involved in manufacturing. It's pretty cool. The last one, we talked a little bit about discrete element modeling in LS-DYNA. Kind of the leading tool in the Ansys world for that is called Rocky DEM. And our friends and channel partner down in South America, ESSS, did a really good article about how they couple Rocky DEM and Ansys Fluent to model particles flowing in fluid. And it's called using CFD DEM coupling to model non-spherical particle and fluid flow. So these are non-spherical particles, of course, much more difficult. So take a look at that. And if you model particle flow in fluids at all. We didn't add anything to the PADT blog because we're still super busy with new things. Upcoming events, we've got the webinar we spoke about earlier about mechanical solver elements and contact enhancements at Ansys 2019 R3 mechanical and mechanical APDL. That's going to be Wednesday. As I said, go to Bright Talk or to PADTinc.com's the events page to sign up for that on Wednesday. Other events, we'll be holding our big annual Colorado event on the same day on Wednesday, 9/25 from 1 to 7 at Blind Faith Brewing in beautiful downtown Littleton. It's actually just a little bit west of downtown, right up against the river, which is pretty cool. The Platte River, it's a really neat location if you've never been. This is our third year holding it there. We expect about 200 folks to show up, and we will be having some discussions about Ansys simulation, and a few people from Ansys Inc. will be there, as well as our Ansys team in the Rocky Mountain region will be there for to meet with you and talk with you. The following day, we'll be hosting a design for digital light synthesis. That's the carbon technology that we use to do relatively high volume 3D printing. And that's going to be down the street. So check out our website for that. Then in October, which is coming sooner than I'd like to even imagine, it starts up AZ Bio Week here in Arizona, and we will be at the AZ Bio Awards. We actually made the actual awards. That's on October 2nd, and we'll have a booth there. So if you do come to that, stop by and say hi. And then on the 24th is the Arizona Technology Council's Governor's Celebration of Innovation, and that's our annual awards banquet, and we're excited to also make the awards for that, and we'll have a booth as well. So do come to that. It's a great event. It's pretty much everybody in tech in Arizona shows up for that. So please do come on out. And we'll finish up the month at the Tucson Southern Arizona Tech Plus Business Expo on October 30th, which is the big Tech Council event down in Tucson to finish up the year there. And I hope to see lots of people, and do mention that you listen to the podcast when you stop by. That's it. I want to thank you. Don't forget to subscribe to www.padtinc.com/opt-in. Spread the word out there. Let people know about the podcast. Our listenership keeps going up slowly, but I like to see it go up faster. I hope if you find it a good resource, let other people know. That's the only way to get it out there, because we're too cheap to pay for advertising. So don't hesitate to reach out. Let us know what you think. And we hope to have great discussions in the near future with you. Thank you. Thank you for joining us for the All Things Ansys podcast, episode 47. As a reminder, this podcast is not affiliated in any way with Ansys Inc., and the opinions expressed are those of the people on the show only, and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.